we definitely didn't apply. We came together during the coffee break to come up with a few what we thought might be discussion-provoking questions. If folks feel super excited about, kicking off a discussion now, then feel free to do so. Right? We're here to help guide things along. But if somebody has any kind of burning questions or things that they've seen in different talks that they want to put together and play with, feel free to just kind of interrupt now or during the proceedings to do that. But failing any kind of hands or burning questions, I think we're going to start.
All right. Yeah. So we came up.
Oh,
I think I've got the thing.
We're
yeah.
Double act now.
It's really professional.
We can overtalk each other.
Yeah.
Lovely. We're going to argue.
We came up with 4 kind of questions, and if nobody likes any of the 4, then bring up your own, or we can just watch videos. Like you nicely advertised my video, so we can just watch that. But
it's 2 minutes long, so we can watch it 15 times.
Yeah, right. Exactly. That would be great. There we are. That's the first one. It felt a bit to us like there were almost like 2 separate. I mean, I'm partly guilty of this myself. There were almost like 2 separate types of talk this morning. There were ones where we were talking about quenching centrals, and then there were ones where we were talking about quenching satellites. And I'm not sure anybody really tackled the question of how do you connect up these things. I mean, it's all got to be part of a continuum, right? I mean, there may be separate processes that only affect satellites, but clearly satellites were centrals once, and they still feel the same physics. So how does all this connect up? Go.
I don't sympathize with the white thing. I don't think we should stop thinking of this, because as you said, they were centrals, but then they move into a big halo with a hot CGM or something, and something else happens to them. Round pressure stripping, tidal stripping, extra mergers, what have you. And actually, in one of today's talks by Joanna Wu, she pointed out that their quenching track is somewhat different in the environment of the cluster, and actually much more efficient. So I don't want to stop thinking about this. I think we should think about the past and the continuous different evolution.
Can I just respond to that and then give it to, because I definitely want to, is this off? It's off. It's on? Oh, okay. So part of it was, we were inspired into this in part by Joanna's talk, and part of it was that there were some, no offense, some, I think it's off. On? Yeah, it's fine. Okay. There were some, it's hard to take present-day properties of something, to say present-day satellites and present-day centrals, but then remembering that, hey, that when it fell into the environment was a long time ago. We don't have, the comparisons are not being done with centrals at that time. So the point is there's a process, and also the satellites still have stellar feedback. The satellites still would have AGN feedback if they're supposed to have AGN feedback. And it seems like the processes that we think about with centrals, we suddenly stop thinking about them acting on the satellite when they become a satellite, and we think that's probably oversimplified. And so this is what we wanted to, we have no objection to the extra environment process, but we just thought that it's maybe being oversimplified, the thinking about it right now. Joanna, go ahead. No offense.
None taken.
You gotta start somewhere.
So I didn't show this today, but what I had shown today were the effects at the lowest masses. But actually, we do find that there are effects at the highest masses as well. They're much weaker than for the lowest masses, but you also see differences in the SSFR versus sigma 1 diagram at the highest masses around 10 to the 10.5 to 11 range. So it may indicate that even if you've been pre-processed, you still feel a little bit of an effect from the environment.
I just wanted to say that I think we should keep our eye on the ball with regard to this paper, because it's been remarkably hard to find explicit smoking gun evidence for environmental quenching. I mean, there are some exceptions. There's ram pressure stripping in Virgo, and but just looking at galaxies and clusters generally, yes, the statistics are there, but you look at the individual galaxies and they look, you can't tell what happened to them. So I think the significance of this is the fact that actually a different quenching route has been identified for the vast majority of galaxies. It varies as a function of environment, kind of in the way you would think. And yes, what we see is a mixture of what happened in the past and what's happening today. And, I'm going to take refuge in the classic, it's beyond the scope of this paper, to figure that all out. I think it's kind of elaborate. We'll take careful modeling.
So Avishai had something, but just to check if there's others who want to. Joel? Sorry.
Well, since there's so many people here who have spoken today about the black hole mass, galaxy, and star formation connection, I'd like to go back to a topic that Chung-Pei Ma raised. There are these extreme outliers, like NGC 1600. What's the story with them? In particular, the ones with super high black hole mass to stellar mass or stellar velocity dispersion. And are they equally high above the expected correlation with velocity dispersion as they are with respect to stellar mass? I think my impression is that it's much more extreme with stellar mass, less extreme with velocity dispersion. This could be a clue as to what's going on. But coming back to this issue of which you also raised, Eric, in your talk, but didn't say much about it. What's giving rise to this big dispersion, in particular the really extreme outliers?
So we've got two separate topics going. Did you want to close the loop on the first? Yeah, let's close the loop on the previous topic before.
I think the strongest point on this is the fact that, as Joanna showed, the quench fraction of satellites of the same mass as a field galaxy is much higher. And this by itself tells you that satellite quenching adds very important quenching process to galaxies.
Okay. Are there any responses to the issue of thinking about the drivers of scatter and black hole mass as a function of stuff? Right, stellar mass. Go ahead. Yeah.
It's clear that to form the black hole mass, you have to have the gas go to the very central region. So I still think that the way the gas comes in and the angular momentum makes a difference as to how much actually gets converted. So if you're extremely lucky, let's say maybe 1600 was in a group such that the chunk of gas in its neighboring galaxy just happened to come in such a way that it plowed, it had a very low angular momentum, and it just funnel right to the middle. I'm sure the theorists can come up with some sort of merger where there's an extra amount of gas goes in the middle region compared to others which have different angular momentum, and those can provide some variety. And I don't know what it is for 1600, but I'm just saying that we need to think maybe into another parameter space where the angular momentum of the gas and the amount of the gas that goes in the middle region is what determines the final one. And of course, we as observers look at things and we have statistical distributions and their correlations, but the dispersion in the end does make a big difference in the way we view what the whole process really involves.
Why doesn't it form stars? The amount of angular momentum you've got to get rid of to get into the black hole is
Yes.
enormously larger than what you need to do to make stars. So why do you get this huge ratio, 10 times higher black hole mass and stellar mass for this particular object compared to most objects?
Well, if I understand correctly, the major mergers, depending upon exactly how they come in, disturbs things in such a way that it could perturb the central disks that are forming, right? I mean, we can see that the minor mergers don't do things, at least from the merger simulation we saw today. So if those things activate, if you look at enough major mergers, I think you will find that there are differences in the final amount of the black hole mass compared to the amount that's formed in the bulge or the stellar component. Whatever that dispersion is, focus on figuring out what that component is. And I would guess it could come up with factors of 10, but it'd be rare. It has to be exactly the right way of the mergers coming in. But it's up to you guys, the theorists, to come up, to look for these. I'm just saying that there's another parameter that clearly comes into play. It's not that everything comes into one parameter. It's not scaled with small dispersion. It's a big dispersion.
I kind of want to jump in because we just saw this really nice example in the manga survey, right, where you've lost a disk. It's no longer there, and what you have instead is some turbulent mess. And that's completely what we see in our simulations, actually, that, you know, we have this very nice controlled test because the gas is funneling down the same filament, so it's coming in with the same angular momentum. We can actually check that directly, and it's true. And when you have that enhanced merger case, you go into a mode that looks just like that manga example, where you have a whole load of hot gas. It's just sloshing around in a very chaotic, turbulent way. And it can very easily just grab gas that's coming in and either shock heat it and get rid of it or sweep it into the black hole. And so you can switch modes and switch from a mode where the incoming cold gas goes into stars into a mode where it just, a trace of it goes into the black hole. And that's all you need to do, I think, to explain these kind of situations.
Okay, it looks like we're able to transition, and it's good. Now, this one is Andrew's fault, so, but I think it's funny, so we're going to go for it. Does anyone still believe in quenching, quasar mode quenching? Does anyone still believe? Does anyone believe that in the high Eddington accretion, that quasar mode, the high Eddington accretion is the thing that quenches galaxies, that quenches star formation in galaxies? Right? Or are we all super happy with the idea? I mean, the alternative would be, for example, maintenance mode, AGN feedback, or whatever other tooth fairy du jour you're interested in. So the question is, you know, so we wanted to, this is an unusually annoying way to ask this, but we wanted to really kind of get at the idea of what is the role of this, because we saw earlier on, Stephanie was showing us that quasars tend to be rather star-formed.
Can I just make a comment?
Well, so I think there was Sandy, you were looking quite urgent, and then Joel, so you're going to go after. Then somebody else.
I was looking for clarification.
Oh.
You've sort of mixed modes on me. You're talking about quasars and also high Eddington.
And using the two as synonymous.
Oh, okay.
High Eddington accretion making essentially radiated outflow, as the theorists would like, as opposed to the essentially kinetic
Okay.
feedback.
No comment.
So what I wanted to do was...
Still U versus Fabian, right?
Okay.
So I wanted to just mention, in order to smoke out some people who actually may believe, or at least include in their models, the high Eddington AGN, that there are 3 different classes of semi-analytic models. There may also be different classes of simulations, but I've been involved in the semi-analytic model side of this one. So the Santa Cruz semi-analytic model that originated with Rachel Somerville and me, and then later on with Phil Hopkins and others, included AGN. That's definitely of this type. It has the quasar mode, quite explicitly, and it has maintenance mode. The guy who introduced the idea of radio mode or maintenance mode has never included the quasar mode. So it's only maintenance mode. And there are also semi-analytic models that include neither one. Yu Lu, who's here, has a model that didn't include either one. And all actually can do a pretty good job of matching low redshift data. But just to mention explicitly that there are people here, like Ryan Brennan, although we didn't talk about the semi-analytic model, or Viraj Panja, who are co-authors of recent papers that include quasar mode. You can ask them to defend it or not. But there are certainly people here whose models include it, including me, but I'm not going to particularly defend it because I know that there are big uncertainties.
You got
So, yes, I'd like to comment a bit more on the observational side. And I think quasars and the high Eddington AGN mode is very good at making outflows, which is not the same as quenching. But it could be that there's a bit of a local quenching, for example, like an inside out or making a hole. So some IFU work, for example, I found suppressed star formation locally in a galaxy where the outflows are fast and probably ionized wind. But still, it could be that it's not very efficient at quenching the entire galaxy. So maybe you can make a hole in the middle without quenching the whole thing. And also there's, well, some people claim evidence of both negative and positive feedback. So it's not clear if the triggered star formation from the compression from the shocks and the winds can compensate from the locally suppressed star formation. So it could be that it's more messy and it's not just a yes or no question. I win.
No, you wins. No, just.
I just want to give some comments on semi-analytical model set. I don't mean to defend myself or the idea of not including AGN as a quenching mechanism in semi-analytical model. I guess just different modelers have a different approach to the problem of galaxy formation, and the approach I have been using is start with as simple as possible model and try to constrain such a simplest model to observations and see where we have to make changes. I guess a halo quenching, as Joe correctly pointed out, even though we start with very simple model without any AGN, just halo quenching, we can successfully reproduce several observational constraints at the local universe. It's certainly interesting to look into what type of observation can give strong constraint to understand questions like this. But it's not clear to me yet which observation really give you very strong constraint to answer this question. I think for observers, maybe this is a good question for you guys and to communicate with theorists to figure out what type of observation can really help us out.
Anybody else want to come in on that? Okay, no. It's going to look like that was a plant now, because our next question was exactly about intuition building models, which I think is a little bit connected to what you were just saying, that if you build simple models and then see how they match up with observations, you get some kind of intuition. So we were thinking that there have been several talks over the last few days that show these at various different levels of detail, and the kind of models that we're thinking of, classic like bathtub models. Many people have made models of the cusp core transition process, closed box metal enrichment models, cooling shock stability models, and now seems like a heroic effort's going on to look at what makes cold streams stable or unstable. So we wondered, it seems like not every problem is open to attack in this way, because something's just crazily complicated the way that everything ends up interacting. So what is the next problem that's really open to this kind of vector of attack?
And I think just to add to it, the context is that we often come with very simplified models, right? And I've done it, and a number of other people have done it. You start with something simple, but they're often not grounded in. They wouldn't pass muster of, hey, does this even look like a hydrodynamical simulation? Is it attempting to capture some of what was happening? When we've actually attempted to, hand on heart, do your best, include a number of important physical processes in one's thinking. So it's really a kind of intuition building, but cognizant, or trying to capture the essence of what's happening in these much more complicated models that you just kind of run and then say, hey, or this is what happened, but you don't necessarily know why. So what are the next frontiers for this? Thoughts? Go ahead.
I can point at two things that I myself find challenging and exciting. One of them, Eric and others today and yesterday talked about mergers as a paradigm for making things like AGNs and changing morphology and so on. My thinking is that there's a broader phenomena which results from mergers, but also from other processes when galaxies form in the cosmic web. And this is what I like to call wet compaction of a galaxy, of the gas in the galaxy. Now, mergers certainly do this. They push gas in dramatically, but other things can do it, like when you have streams feeding a galaxy and some of them are counter-rotating, you end up with cancellation of angular momentum at some points, and you can end up with wet compaction. It can happen also because of some fountain phenomena that plays with more or less angular momentum. And there are other ideas. And I'm not sure what I know what they are. There are many of them. Mergers are very important ones. So this is for me an open intuition building model.
I don't think what I'll say as ideas for intuition building models is a new thing, but I think it's something that people are considering ongoing, and I think it's very fruitful. And the two things that I think are very fruitful are in the context of bathtub model, although different people mean different things by what bathtub model is. It's just a system of differential equations that bookkeep various things about the galaxies in the context of halo evolution. The two things I think could be amenable to intuition building models are the total metal budget in the galaxy and CGM together in different components, meaning gas, stars, and dust. Overall, the dust formation model, I think, is very fruitful in the context of this type of intuition building model, because one thing that comes out from these models is that you cannot build dust content of galaxies with just supernovae and AGB, and you need growth of dust in interstellar medium. And if you talk to people who actually study dust formation for a living, they'll tell you that there are no known processes by which dust forms an interstellar medium. And I think this is a very fruitful and interesting clash of intuition building model and what people know about dust formation.
Any other intuition to build? I'll run. I gotta get some exercise.
I've been intrigued by the idea that a lot of things get pre-processed, but I didn't really see any simulation showing that as a group falls into a rich cluster of hot gas, whether the whole group's, call it its bathtub that provides for the galaxies that otherwise are in the group, actually get wiped out or harassed, etc. Usually the mechanisms for satellites are for individual satellites rather than as part of a group. And I was just curious whether that's been done and I just haven't seen them, or it doesn't matter, or whatever. Hopefully the theorists understand my question well enough to answer.
Does anyone have an answer?
Why? Why no answer? What happens when a group with some amount of, what happens when a group falls into a cluster? What happens to the group's gas in terms of ram pressure, could be even tidal stripping, et cetera, et cetera. What's this pre-processing, and how effective is that pre-processing? I didn't get a sense of that in listening to the talks this week so far.
Yeah, at some level it's kind of the version of that. Right? It's really trying to account for the full history of galaxies as they're following.
Well, short answer to part of that question, in what I showed in this morning, so I was talking about satellites, but I did check to see how halos of mass, if you look at the mass of satellite to cluster, even of about like 1 to 100, which is roughly what a group would be, a 10 to the 13 group falling into a 10 to the 15 cluster, you still get a lot of mass removal around the virial radius. So maybe not as much as 90%, but you can still remove maybe half or 70% of the gas from a group-sized group-sized system falling into a cluster at the virial radius roughly. So that's ram pressure stripping alone. Other things might do more. So at least that part, I mean, you can affect group-sized systems inside clusters in that sense.
Call that reprocessing.
Well, no, I would just call it stripping.
Should we move on?
Sure. So we have technically 5 minutes left, right?
I don't know.
We don't have to use it all, though.
No.
But we had one more question. This is a bit off the wall, so let's see what people make of it.
All our other questions have been fine.
They've been fine, yeah. So we were, we've had a few talks about black holes, both kind of stellar mass or 30 stellar mass black holes and supermassive black holes. And these, of course, now look very different to what they would have looked like this time last year. So what are people's hopes for what we're actually going to learn from gravitational wave astronomy? Is it going to be just a curiosity, or are we actually going to learn something fundamental about galaxy evolution? Somebody must have an opinion. We have a room full of people with strong opinions. No one has an opinion. Yes, what? Yes,
Yes,
what?
what?
Go on, tell us.
I have no idea. Yes, we can learn about black hole merger rate. That's.
But do you care? Do you care what the black hole
I
merger
care
rate
very
is?
much.
Okay.
Well, one of the things that we're going to learn from the number of these high mass mergers, like the first one that LIGO found, is how common those are. And very likely, I think, those are mergers of stars that formed early in the universe at very low metallicity. Maybe some of them formed later at low metallicity, but certainly most of the low metallicity star formation should have occurred in the early universe. And actually getting a quantification of that would be very interesting. Of course, we're also testing general relativity. Another thing that we're going to learn from LISA, there are two big things we learn from LISA when LISA finally gets funded and goes up, which we hope is not going to be in the 2030s, but maybe gets sped up if the United States rejoins the LISA project. But anyway, the two big things we learn is the merger rate of intermediately massive black holes, and from the ground-based radio telescope observations, we can get even the more massive black holes from the pulsar array timing. And that will really tell us, among other things, whether the black holes merge. It's a big question, what drives the black holes together once they're just a parsec apart, the final parsec problem. We know that if there's enough gas, that can probably make them merge. Another interesting question is, does that align their angular momenta so that they don't get the huge kicks? Because another mystery is, if they're the big kicks, why do we always find massive black holes in the centers of massive galaxies? The other thing we can learn from LISA, or ELISA, is there'll be a very large number of high mass ratio mergers. And those let us probe with incredible precision the exact nature of the Schwarzschild or Kerr metric and verify general relativity. And then the other thing we get from the big merger, black hole mergers, is we get an extremely accurate distance measurement, which in principle can be 1% in each object. And there's no other way that I'm aware of where we could get distance measurements like that to systems that are many megaparsecs or even gigaparsecs away. So those are all wonderful things that we can get from these gravity wave observations. I was one of the members, I was the senior cosmologist on the so-called Beyond Einstein National Academy study, and we explained all these things. I'm just remembering the things we said. Yeah, the merger, well, the merger rate of these massive black holes, assuming that they merge, because you don't get the gravity waves until they finally merge, will tell us the rate of formation and evolution of these merging black holes. So yeah.
Okay, so we got Michael, and then this gentleman up here, and then James, and then David.
So, as I alluded to a little bit in my talk, I think that LISA, as well as, I should mention, pulsar timing is actually something that's currently being used as well to, as that gets better, we'll learn also more about supermassive black hole mergers beyond just LISA. I think that information combined with simulations, combined with analytic models for merger rates of black holes tethered to merger rates of galaxies can actually give us a really good idea of how black holes and galaxies co-evolve. In particular, it can give us an idea of, is it black hole mergers that are driving the seed mass black holes to grow, onto the M sigma relation for lower mass galaxies? Or do they grow via accreting gas? Things like that. And I think as Joel sort of hit on, in general, looking at the population of black hole mergers over time, LISA and also pulsar timing can give us an idea of what is the seed mass of black holes, which can give us formation criteria for for supermassive black hole seeds, which then can help us learn about which galaxies host black holes, not just the most massive ones, but going down to dwarf-sized galaxies, which is sort of, I think, at the forefront of where we're at understanding galaxy black hole coevolution, the lower mass end.
Yeah, so I think as far as supermassive black holes, we are going to get a lot more out of pulsar timing arrays than LIGO in particular. LISA might give us an estimate of what happens early on in the long wavelength regime, as I understand, but PTAs are probably the way to go forward there. As far as galaxies, what can we learn about galaxies from LIGO versus, say, stellar physics and how low metallicity stars evolve and how massive stars are able to hold on to their mass? I think, Joel, you're pretty spot on that it gives us an indication of where the low metallicity gas is and what it's doing, whether it's forming stars and whether those stars are forming in binaries in particular. We don't really know anything about the binary fraction at the high mass end, except maybe it's 0.5, maybe it's 1, maybe it's 0. Well, 0.1.
Yeah, so I would just add to that. I think, in principle, it depends on what we find, right? I mean, so if it's to the point where you could have an array and triangulate where some of these mergers are happening, especially at the very high mass end, it could be interesting. For example, if the Feynman slope of the stellar mass functions gets steeper, that would show up. So some of the things that Oliver didn't have time to show is that some of those distributions change if you just impose something Feyn at the arising in the stellar mass function at the Feyn end. If the IMF varies with stellar mass dramatically, you could see this, especially at the high mass end. 50 solar mass black holes, right? That's going to be sensitive to these kind of changes. So in principle, if you get enough of these, you could try to figure out where their hosts are. We could start to try to put this stuff together. I mean, it's many pieces down the line, but it could be really fun to see what LIGO sees.
I think we're out of time, so unless anybody has any burning comments? Nope. Time for a beer.
Just then to thank all of today's speakers, except for Andrew.